Taking flight. It's the stuff dreams are made of. And it says something about us as a species, that we once looked at the birds soaring in the sky and said, bet we could do that. But in spite of our lack of wings and feathers, we did. And we didn't stop there. Once in the sky, we found a new limitation above us, space, a place where all the air ran out. And in spite of our very real need to breathe, we thought, bet we could go there. And we did, sitting on top of controlled explosions that we named rockets, all the way to the moon. Humans apparently don't like being told we have limits. But soon, the age of combustion rockets will be over too. They burn up their fuel too quickly, and using them for travel to the places we're thinking of going, like Mars, or even other stars, will simply take too long. And so, new technologies are needed. But what will get us there this time? For journeys that could take months or even generations to complete, what solutions could help us bridge such gaps? The exciting part is, the answers are in development. And it turns out these new ideas are even crazier than rockets. I'm Alex McColgan and you're watching Astrum. Join me in this video as we explore the future of space travel, from the next generation solutions that are just around the corner to the proposals that feel science fiction, but could one day become science reality. It's only in the last 100 years that humanity has truly begun to venture into space. On the 16th of March 1926, Robert Goddard, the father of American rocketry, launched the world's first liquid-fueled rocket on a farm in Auburn, Massachusetts. It may have only reached about 12.5 meters and was done to little fanfare, but this moment was the beginning of 100 years of chemical-powered rocketry that ultimately let man walk on the moon. Understanding where we came from is important in understanding where we're going. So let's take a closer look at chemical rockets. Here, thrust is generated by mixing some kind of fuel source, often RP1 kerosene, or other variations refined from crude oil with some kind of oxygen source. For instance, pure oxygen in liquid form in a combustion chamber and then igniting them. Hot things expand, and in such an explosion as this, they expand a lot. A chemical rocket points that explosion downwards. Then, thanks to Newton's third law, where every action has an equal and opposite reaction, the rocket as a whole goes up. Chemical rockets have been the key driving factor in more than 7,000 launches globally since the dawn of the space race in 1957. And even in space itself, chemical propulsion methods, whether burning fuel in thrusters or just spraying compressed coal gas out of a nozzle to get a little extra oomph at the right moment, are the primary way that probes and spacecraft have explored the various planets, moons and asteroids that make up our solar system. But chemical propulsion has a big problem. While it's very good at the short-term challenge of punching its way free of the Earth's gravity, a task that requires a large amount of force to be applied over the course of just 8 or so minutes, and a little light maneuvering to enter orbit around a planet, they are just not efficient, and so run out of fuel quickly. For instance, let's take a look at this Falcon 9 rocket, the kind favored by SpaceX in their hundreds of launches. While a Falcon 9 rocket has 549,054 kilograms of mass at launch, 395,700 kilograms of this mass is fuel. This leaves very little room on any rocket for the payload, or the part of the rocket you're actually trying to get into space in the first place. Why is so much fuel needed? The answer is in a chemical rocket's specific impulse, which is a measure in seconds of how much thrust you get for each unit of propellant. Think of it like the fuel economy of a spacecraft. While rockets are able to generate a lot of thrust, their specific impulse is quite low, never much higher than 500 seconds. They are like lightning fast sports cars with really bad mileage. They can do very powerful bursts, but will then quickly need to top up at the nearest fuel station. Sadly, we don't have many of those in space yet. Which brings us to the next currently existing technology, one which has almost the complete opposite problem: electric thrusters. While not as commonly used as chemical thrusters, electric thrusters have seen use in missions like NASA's Dawn mission to the asteroid belt and by SpaceX's Starlink satellites. And by some metrics, these engines are impressive. Electrical or ion thrusters can have a specific impulse up to 10 times higher than chemical propulsion, allowing for far longer journeys or greater overall acceleration compared to their chemical counterparts. Electric thrusters come in many different types, but all work via Newton's third law, just like chemical rockets, pushing propellant out to push the rocket in the opposite direction. However, while chemical propulsion relies on hot reactions to produce their thrust, electrical thrusters, like the Hall effect thruster or the gridded ion thruster, work by creating electric or magnetic fields. Particles of noble gases like xenon or krypton are accelerated in these fields up to speeds of 140,000 kilometers an hour in ion thrusters, though less for Hall thrusters, and are sent flying off into space. When the particles accelerate one way, the spacecraft is pushed the other way. This is the advantage of electric thrusters in general. If you're accelerating your fuel up to 140,000 kilometers per hour, you're getting some really good mileage for each atom accelerated. When it comes to most thrusters, a key principle towards understanding them is momentum. And the thing with momentum is, if you don't know where to start with it, it can be hard to get the ball rolling. When I was studying at uni and was finding myself as stuck as an object at rest, I sometimes needed a helping hand to become an object in motion. For me, that didn't come from reading textbooks, it came from practice, testing my understanding with questions that forced me to engage my brain, which is why I really like Brilliant, today's sponsor. Brilliant has thousands of online lessons with interactive questions that get you thinking. It has courses on maths, coding, and even momentum, like this fun lesson that uses pool to teach physics principles. It's great for helping you study, whether you're young or old, a student or a parent looking to help their kids. Brilliant's courses are developed by top researchers at MIT, Harvard, and Stanford, so go try them out today by scanning my QR code or following my link brilliant.org/astrum in the description below. There's a 30-day free trial, and my viewers also get 20% off an annual premium subscription, which gives you unlimited access to everything Brilliant has to offer. See if it gives you a little momentum too. Now, back to the pros and cons of electric thrusters. With all that acceleration, surely electric thrusters are just better then? Well, actually, no. There is a downside, a significant one. You see, electric thrusters actually have terrible thrust. Think of it like putting your thumb over the nozzle of a hose. By limiting the hole the water is coming through, the stream of water coming out of the hose turns into a powerful jet. But removing your thumb to create a bigger hole does not mean you get an even bigger jet. You only have so much water to work with. For electric thrusters, the problem is similar, except instead of water, it's electricity. Electric thrusters connected to a solar panel can get plenty of energy if you leave them to run for long enough in sufficient sunlight, but you don't get that energy all at once. You have a limit on how much fuel can be accelerated based on the electricity you get in a given moment. So, how little thrust are we talking about here? How much can electric thrusters generate? It turns out, about the same amount of force as you'd feel from the gravity of a piece of paper lying flat on your hand. It can take days for an electric thruster to accelerate a spacecraft to just 90 kilometers per hour. And while it can get up to 320,000 kilometers per hour eventually, as NASA had considered doing on future missions to Mars, if there's any friction or opposition to its movement, an electric thruster won't ever get off the ground. Don't use one of these to try and launch a rocket. Electric thrusters are good in marathons, not sprints. Still, neither of these technologies are currently suitable for the types of travel that humanity wants to eventually do around the solar system and beyond. Because chemical rockets use up their fuel so quickly, they can't actually accelerate for very long and thus don't attain a good top speed. Electric thrusters have a good top speed, but accelerating is a slow process. And once humans start ferrying large numbers of crews, machinery, and raw materials to places like Mars, the amount of mass needing to be accelerated is just too much. And of course, electric thrusters will eventually run out of fuel too. So, what is the future of space travel? It's time to look at some of the contenders. Before I show you what NASA is developing, I want to give an honorable mention to a technology that I find really cool. Japanese company Obayashi is planning on finishing off a real-life space elevator by as soon as 2050. While not strictly a means of traveling through space, a space elevator is a fascinating alternative way to get something into space with a fraction of the energy costs that a chemical rocket has to expend. The principle behind them is simple. All you would need is some kind of anchor, a space station or an asteroid that was orbiting the Earth in a perfect geostationary orbit. Then you dangle a cable down from that anchor until it reaches the ground. Finally, just put